Hello everyone, welcome to today's class. The topic that we are going to see today is traditional symmetric key ciphers part 1. Now let us take a look at the general structure of the symmetric key cipher. So as you can see here, we have Alice and Bob. So Alice wants to send a message to Bob. Now Alice will construct this plain text, and using an encryption algorithm and a secret key, Alice will convert this plain text into this ciphertext, right? Then Alice will send this ciphertext along an insecure channel, and Bob will receive this ciphertext. So after Bob receives this ciphertext, Bob will use a decryption algorithm and a shared key. So this key is the same key that Alice used while encrypting. So Bob will use the same key and a decryption algorithm to convert this ciphertext into the plain text. And that is how Alice and Bob can communicate using the symmetric key cipher. So the main principle of this symmetric key cipher is that Alice and Bob both use a secret key which are same. Okay, so let us see this diagram. Now in this diagram, as you can see, the encryption algorithm uses this lock to basically lock this key, and this decryption algorithm uses the same lock to open this key. So this same analogy is used in this method as well. Now here you can see there is a Kirchhoff's principle. So Kirchhoff principle states that only the key should be kept secret. The encryption algorithm and decryption algorithm does not need to be kept secret. Only the key that is shared between Alice and Bob needs to be kept secret. Okay, so it needs to be kept secret from all the adversaries. Okay, so that is what Kirchhoff's principle states. So this is basically told because we need to assume that any attacker in any networking regime can know the encryption algorithm or decryption algorithm by one means or the other. So the main principle for this method should be to keep the key secret. All right, so say for example, we have a group of 4 people, okay, and these 4 people, 1, 2, 3, and 4, they want to communicate with each other using this method. So how many keys are required for this purpose? So when one will want to communicate with 2, okay, and again when one wants to communicate with 3, they need to use a key which is unique to them, right, which is unique for this communication. So we can see if one wants to communicate with these 3 people, it needs m minus 1 keys, right? Now how many people are there? Say for example, m is equals to 4. So if one wants to communicate with these 3 people, it needs m minus 1 keys, right? So how many people are here? There are m people, right? So since there are m people, so they will require m into m minus 1 divided by 2 keys. Okay, we are dividing it by 2 because we want to cancel out the duplicate calculations that fall into this m into m minus 1. So the total number of keys required by a group of people to communicate is m into m minus 1 divided by 2. So as cryptography is the science and art of creating secret codes, cryptanalysis is the science and art of breaking those codes. So cryptanalysis is important for finding how vulnerable our crypto system is. There are 4 common types of cryptanalysis. So they are the ciphertext only, the known plain text, the chosen plain text, and the chosen ciphertext. So these are the cryptanalysis attacks that we'll be seeing. So the first cryptanalysis attack is the ciphertext only attacks. Okay, and in this ciphertext only attack, what happens? The adversary tries to find the corresponding key. Okay, so in this ciphertext only attack, the adversary will try to find out the key so that it can generate the plain text from the ciphertext. Okay, now it is of 2 or more types. Okay, so we see that the first type is the brute force attack. So this brute force method or the exhaustive key search method is used by an attacker to search for the plain text by using every possible key. Okay, to search for every possible key. So next is the statistical attack. Now there are some properties in language which the attackers can take advantage of. Say for example, the letter E has the highest frequency of occurring in the English language. So taking advantage of these properties of any language, adversaries can launch this statistical attack. Again, in the ciphertext, there might be some patterns. Okay, so if the attacker or an adversary can decipher those patterns, then they can launch this pattern attack. Moving on to the known plaintext attack. So in this scenario, what happens is the adversary has access to the plaintext and ciphertext pairs from previous scenarios. So say for example, Alice and Bob are communicating. Okay, so after they have communicated, okay, they have revealed the contents of their communication. So what happens is the attacker will try to store the already publicized ciphertext or plain text, okay, that has been revealed by their first communication. Then what will happen is, again, when they will try to communicate, Alice when will try to communicate, the adversary, say the adversary is Eve will try to match the previous scenarios plain text and ciphertext, okay, that Alice and Bob communicated. So launching an attack in this manner is known as the known plaintext attack. Then moving on to the chosen plaintext attack, we see that here the adversaries themselves choose the plaintext ciphertext pairs by accessing the sender's computer. So if any adversary has access to the sender's computer, then they can launch this plaintext attack by themselves choosing the plaintext and ciphertext pairs. Now, if the adversaries have access to the receiver's computer, then they can choose the ciphertext plaintext pairs, which is known as the chosen ciphertext attack. So these are the four kinds of attacks that adversaries can launch, okay, for cryptanalysis of the ciphertext. Now moving on to the categories of our traditional ciphers. So the traditional ciphers can be divided into two parts, one of which is the substitution cipher and then is the transposition cipher. So this substitution cipher can be divided or categorized into two types again. So they are the monoalphabetic cipher and the polyalphabetic cipher. Now this monoalphabetic cipher can be divided into the Caesar cipher, the multiplicative cipher, the affine cipher. And this polyalphabetic cipher can be divided into the Auto-key cipher, Playfair cipher, Vigenère cipher, and Hill cipher. There are other polyalphabetic ciphers, but we are going to see only this four now. Then for the transposition cipher, we have this transposition cipher can be divided into two parts. One is the keyless and another is the keyed transposition cipher. So moving on, we will see what all of the ciphers do and how they work. So firstly, let us see what substitution ciphers are. So a substitution cipher replaces one symbol with another. So if the symbols in the plain text are alphabetic characters, we replace one character with another. Okay. So for example, we can replace the letter A with letter D and letter T with letter Z. So if the symbols are digits 0 to 9, we can replace 3 with 7 and 2 with 6. Okay, so this manner of replacing characters, replacing one character with another is known as our substitution cipher. So this substitution ciphers, as I have already previously mentioned, can be categorized as either monoalphabetic ciphers or polyalphabetic ciphers. Now we will see what these monoalphabetic ciphers are. A character or a symbol in the plaintext is always changed to the same character or symbol in the ciphertext, regardless of its position in the text. So for example, if the algorithm says that the letter A in the plaintext is changed to letter D, every letter A in the plaintext is now going to be changed to the letter D in our ciphertext. So in other words, the relationship between letters in the plain text and the ciphertext is a one-to-one relationship. So these monoalphabetic ciphers, as I have already previously mentioned, can be categorized into Caesar or additive ciphers, multiplicative ciphers, and the affine ciphers. So let us first take a look at what these Caesar ciphers are. So the Caesar or additive ciphers. Now, this scissor or additive cipher is sometimes referred to as the shift cipher. Now, this representation of cipher and the plaintext are given in this diagram. So as you can see, for our assumption's sake, we have given the plaintext in lowercase letters and the ciphertext in uppercase letters. So now on, we are going to always represent our plaintext in lowercase letters and the ciphertext as uppercase letters. And the values of those plaintext and ciphertext is given here. So the values of A will start from 0 instead of 1. And as it goes forward up to Z or Z, it will end at 25. Okay, so the numbering is done from 0 to 25, right? And as you can see, B and B has 0, 1, C has 0, 2, D has 0, 3, and it goes on. Okay, now from this diagram, we can see that Alice is sending a message to Bob by encrypting, right? Now here you see that this ciphertext C is the ciphertext, P is the plain text, and K is the key that we are using in our encryption algorithm, right? So how is this ciphertext generated from the plain text P? So here what we do is we take the plain text, individual character of the plain text, and we add it with the key, and we do the mod operation with 26. Now why are we modding it with 26? Because we need the ciphertext to always remain between 0 to 25, right? You see the values are from 0 to 25. That is why we are doing a mod operation of 26, so that the ciphertext that is generated will have a value from either 0 to 25. Okay, so after this ciphertext has been generated, now how to decrypt this? So as you can see, the encryption and decryption are inverse of each other. I mean that they should always be inverse of each other. Okay, so the encryption and decryption process, they should be inverse of each other. Why they should be inverse? Because if you want to get the plain text at Bob's end, okay, that Alice wanted to send initially, so if you want to maintain the integrity of this plain text, the encryption and decryption algorithm must always be inverse of each other. Now, as you can see, how is this being inverse? We are using the ciphertext, and we are using here minus k. Okay, so if we do this minus k, this is the additive inverse of the key that we are using here. So minus k is the additive inverse of the key k. Okay, so what we do, we subtract k from C and mod it with 26. So that is how we can get the plain text. So we are going to see this through an example as well. Now let us see what are the attacks this method, this scissor cipher or additive cipher, can have. So this scissor cipher is susceptible to the brute force or statistical attacks, right? So the key domain is very small, which is why it is susceptible to the brute force attack. And attackers can also launch statistical attacks, because in this scissor cipher, what is happening is one character is always changed to that same character in that ciphertext. So this has a one-to-one relationship, right? So an attacker can use, say, the frequency of character occurrence like ETA, which has the highest frequency in English language, or also the attacker can use some character combination of diagram or trigrams like TH, THE, he, ING. So these are some of the diagrams and trigrams which are most frequently used in English language. So using this frequency occurrences, attackers can launch these statistical attacks. Now let us see an example of this scissor or additive cipher. So here, as you can see, we have been given the value of k. Now we are told to encrypt the message hello. Okay, so we are told to encrypt the message hello. So what is given here? You can see that for h, the value is 07 and the key is 15. So what we basically need to do is we need to add 07 with 15, right, and mod it with 26, because our formula says if you want to generate the ciphertext, then you have to take the plain text and the value of the key and then mod it with 26. So what will this give us? Basically this will give us 7 plus 15 is 22, right? So this will give us 22. Okay, so let us see how is this being done. So h, the value of h is 07. So in encryption, we take the plain text, which is 07, and we then take the key, which is 15, and then we do the mod operation, and then the result will give us the ciphertext. So similarly for E, we see the value of E is 4 here, right? 4. So we add 4 with 15, okay, and mod it with 26. So what do we get? 4 plus 15 is 19, and 19 mod 26 is 19. So in ciphertext, what is 19? 19 is T, right? So we give here T. Okay, so in this manner we figure out what are the plain text values, okay, and then we add them with the key that we are given, and then we mod it. In that way we generate the ciphertext. So the generated ciphertext here we have is WTAAD for the hello plain text. Okay, now moving on to the multiplicative cipher. So as the name suggests, here, the name suggests that it is a multiplicative cipher. So what we do while generating the ciphertext is we use the plain text and multiply that with the key that we are given, and then we mod it. So this is the only difference in the Caesar cipher and the multiplicative cipher, between the Caesar cipher and the multiplicative cipher, right? So one thing that you need to notice is in decryption, the key for decryption should be k minus 1, okay, k to the power minus 1. So this is the multiplicative inverse. Now the selected key, that the key that we are selecting, it should have a multiplicative inverse modulo 26. So if it doesn't have a multiplicative inverse, then we cannot use that k for encryption and decryption. Okay, so this k must have a multiplicative inverse. So why should it have a multiplicative inverse? This is done so that we can guarantee that the encryption and decryption are inverses of each other. Okay, so if they are not inverses of each other, then the plaintext that is generated at Bob's end will not maintain integrity. I mean, say the plaintext here says ABC, and here it will say ADF, something like that. Okay, if k is not if k doesn't have a multiplicative inverse. Now, keys with multiplicative inverses under 26 are this keys. Okay, so I have given 12 keys here. So there under 26 we have a total of 12 keys which have multiplicative inverse. So what are those keys? The keys are 1, 3, 5, 7, 9, 11, 15, 17, 19, 21, 23, 25. So under 26, these are the keys that have multiplicative inverses, and the multiplicative inverses are 1, 9, 21, 15. So for 1 it is 1, right? Because if you multiply 1 with 1, you will get 1 mod 26. It will give you 1, right? And then for 3, what you will get, 3 into 9 is what, 27, right? And 27 mod 26 will give you 1. So multiplicative inverses means that when you multiply them and mod it with 26, the value that you should get should be 1. Okay, and these are the keys and the multiplicative inverses for which you will get the value as 1. Okay, now moving on to the affine cipher. So this affine cipher is basically a combination of our Caesar and multiplicative cipher. So in this diagram, you can see that when Alice is sending the message to Bob, at first Alice converts the plain text, okay, using a multiplicative cipher K1, and then again Alice generates the ciphertext using another key by using the additive cipher, right? So Alice uses another key K2 for the additive cipher. So basically Alice is combining two ciphers. One is the multiplicative cipher and then the additive cipher or the Caesar cipher. Okay, so in this approach we need to follow two rules. So what are these two rules that we need to follow? Now firstly, so each key should have an inverse at the other side of the line. Okay, so here as you can see that K1, okay, so K1 should have an inverse on the other side of the line. So here K1 minus 1 is the multiplicative inverse of K1, and then as you can see K2 should have additive inverse. So here minus k2 is the additive inverse. So minus k2 is the additive inverse of k2. So each key that we are using in our encryption should have a inverse at the other side, which means in the decryption end it should have a key which is inverse of the key that we are using in encryption. Now they are used in reverse order in the encryption and decryption. So say for example, if addition is the last operation in encryption, then subtraction should be the first operation in decryption. Okay. So similarly, if multiplication was the last operation in our encryption, then in our decryption, the multiplicative inverse should have been the first operation. Okay, so these are the two rules that you need to follow in affine cipher, and the cipher text is generated in this manner. So firstly, from this diagram we see that the plain text goes through a multiplicative cipher using the key k1. Okay, and then what we do, we add the key k2, then we mod it with 26. But for plain text generation from the cipher text, we first, since the order is reversed, okay, what we have to do is we use the additive inverse minus k2 and use the Caesar cipher first, and then we use the multiplicative cipher. Then we mod it with 26. So this is how the affine cipher works. Thank you. This will be all for today. Hope you have enjoyed and understood the class.